Okay.
So that should be closer. So we're very happy to have the first lecture of the three-part lecture series by Gordana Todorov on pictures and picture groups. Go ahead, Gordana.
Thank you. Well, thank you very much for giving me this opportunity to talk about pictures and picture groups, and that I can kind of talk in more details than usually, you try to squeeze everything really quickly. So I really appreciate and thank you, of course, for organizing this, and it's an honor for, that you gave me this chance. So I will talk about pictures and picture groups. Of course, I already talked about it. So for people who were in my previous talks, there will be some repetitions, some are not repetitions. It was a bit confusing for me, actually, how, what I should repeat and what I shouldn't repeat. So, okay, so I do apologize if it gets boring, if some details get boring, but it's mostly new today that I will be talking, except for quick review. Okay, so the plan is, well, I want to talk about pictures for groups. I want to talk a little bit about history, which I actually never mentioned, but it does have history. It's the topological history, right? Then I want to just mention this is more kind of, beginning of this work with Kiyoshi and Kent and Jerzy Weyman. Of course, give some general examples. And then I want to point out, which maybe I didn't point out earlier, that each group does have many pictures. And that is what actually it was all used for certain groups. They use many pictures, but also each picture has, each picture is a picture for many groups. So it's not correspondence one-to-one, but given a picture, and this is what we are mostly doing here, given a picture, one special group is called picture group. So picture group is one which uses exactly the generators and exactly the relations which appear in the picture. And then I also want to give some examples of pictures and picture groups for valued quivers, because usually my example was A3. Well, today my example will be A infinity, A tilde infinity, and the other will be valued quiver. So assumption for this talk is Q is a valued quiver. So it really doesn't have to be simply laced. The statements really are for general valued quivers. Now, S will be a certain finite set of indecomposables up to isomorphism. So I will give examples of such things. And of course, if it is a finite, well, it's sets of finite sets, okay? Now, LS will be a picture associated to such S. I will define each one of them. So we have Q, we have collection of modules, we have a picture associated to that collection. And then we have a picture group. As I said, once you have a picture, there is a picture group. So we look at this picture group. Last time or last few times, I talked about semi-invariant picture as being an example of such. But I will be talking also about other pictures which are not just semi-invariant pictures. And now with the picture, we can associate maximal green sequence for the picture. And with the picture group, we can associate Coxeter element of that group. I will define all of these, but that's the basic idea. We have Q, we have collection S, we have the picture group, green sequence, and Coxeter's element. Okay, and then the theorem, and here's the theorem that I will give more, well, not details of the proof, but large part of the proof. So the theorem says, okay, I'm starting with this Q, which I didn't write here. Q is a valued quiver. And it says, let S be a finite subset of indecomposable exceptional modules satisfying condition star, which I will list later. It's not actually too complicated, but I'll write later condition. And then the point is that there is a bijection between maximal green sequences for the picture associated to the set S. So I have finite set S, I have picture associated to S, and I look at maximal green sequences to that picture, and correspondence is with positive expressions of the Coxeter element of the picture group. So everything is about picture and picture group. And then the corollary is when Q is a Dinkin quiver of finite type, and notice since I'm saying modulated or valued, right, then it goes from A through G. I actually like that, you know, usually have all the letters A through G. Then there exists a bijection between maximal green sequences of Q, just the way we know about maximal green sequences, and positive expressions of the Coxeter element, just as we know about Coxeter element. So this is kind of the standard notation in standard terminology. But we actually have this theorem, which is more general, and actually it's quite nice to actually analyze what one gets here. And I will talk towards the end about different possibilities for set, and then what happens actually for the quiver and maximal green sequences for the quiver. Okay, so now let me go and, oh yeah, I said I'll give some history of pictures. Okay, so here's the history. Okay, this is topology. Okay, so Kiyoshi, Gusa, and Kent Orr are topologists. And they proved, and here's the statement, link L is a K-slice if and only if Milnor mu bar invariants of the link are 0 up to that level, up to 2K. Okay, so now just a quick remarks and very kind of simplified version. Links are unions of knots in S3. So Rolf likes to look at knots, so maybe links are unions of knots in S3. Now, being a K-slice, what it means, you attach certain 3 disks or 4 disks, I think 4 disks, and then you eventually want to get a disjoint union of disks. Okay, so being a K-slice is how many times you do this until it kind of becomes simple. That's, my last slide, which I'm not going to go through, but I will attach, is actually Kent send me precise statements for, you know, precise definitions here. So this will be my last slide, which, as I said, I'll just submit, okay? And then these links correspond to pictures. Then we have picture groups. So now we have picture groups for these links, and then this mu bar invariants. Okay, so here they are. So they're elements of the homology of the picture group mod the K commutator of the picture group. So you look at the homology of certain group, and group is really picture group associated to that link L. So it is kind of reasonable that it is related to what we are talking. And furthermore, is that these mu bar invariants are actually higher massive products. And I'm still trying to understand these massive products for the semi-invariant pictures, for the homology of semi-invariant pictures, but these elements are higher massive products. So the way they proved, so it's a topological statement in terms of these mu bar invariants, which are elements of the cohomology or homology, and the computations are done using pictures. And also, the most important among pictures are really semi-invariant pictures. They play a role of certain atoms, and I might talk about that, you know, in one of my next lectures. Okay, so the semi-invariant pictures are really important examples of pictures. Okay, so that is just the history. Okay, now a little bit about beginning of this work. So the work is, I write IOTW, so it's Kiyoshi, Gusa, Kent Orr, me, and Jerzy Weyman. And I just want to point out how the work started. So here's the beginning that I think everybody knows Okay. It's the picture that you always see, right? When you talk about semi-invariants, and this Wayman, Dirksen, Wayman have papers, and in many papers, they had this as the main picture. And it stands for triangles are tilting modules and lines are no extensions, and domains are domains of semi-invariants. And then I was giving a talk on cluster categories. So I had this picture, but then I said, but in cluster categories, we also have our shifted projectives. So I added shifted projectives and completed it so that we can really see cluster tilting objects. So that was in my talk. I just drew that picture like that. And then Kiyoshi was there and he said, but this is the same picture that Kent and I were drawing all this time. So if you take the picture that, started with Jerzy Wayman, I add shifted projectives and you kind of twist it a little bit, you get the picture that they were using to prove their link invariant conjecture. So this was kind of the beginning. That's how four of us started to work. So they're the two topologists and two algebraists. Well, Kiyoshi's, I guess, is also algebraist. So, okay, so that's this. Now let me go to the talk, to the rest of the talk. Okay, so, okay, this is still low key. Okay, so general examples of pictures. Well, first of all, picture, when I defined, it is a subcomplex of a triangulation of a K-sphere. You have to have orientation of K-1 simplices and orientation of K-2 simplices. So I explained last time, or the semi-invariant pictures always do satisfy that, okay? And so examples are, so here I have some semi-invariant pictures, but you can have also something which is not semi-invariant picture or something like this. And today I will be actually using also different pictures, not just semi-invariant pictures, but I will be using different kinds of pictures. And given G, as I mentioned, you can have different pictures, or sometimes you don't use all the generators, you don't use all relations. So given G, so this is just a quick comment about non-unique way, but I want to talk about I want to go to the actual talk, okay? So yeah, I also want to talk about example of a picture for a modulated quiver, okay? So here's my valued quiver. And then to put modulation, we can put R here, C here, C here, and you have to have a bimodule here, and the dimensions are like this. And then you have representations. Of course, you have this, and you have to tensor with the bimodule. And I just drew here the Ausländer-Reiten quiver, where you can see all the modules. So here's simple S1, here's P2, P3, and then here are tau minuses of those. And here's the complete Ausländer-Reiten quiver. And here are all the modules. And you can look at the dimensions of these modules. And you can define the domains of semi-invariants just as we did before. The only thing is you use Euler bilinear form instead of, in bilinear form, you just have to put dij's as part of the bilinear form. And here is the picture. So this is the semi-invariant picture of that. And now I want to point out a few things here. So when we had simply laced quiver, we had two lines here. And in simply laced, you have two lines and you have at most one line here. So in simply laced, either you have commuting relations when you talk about the group, or you have product of 2 is equal to the product of 3. Now, when it is not simply laced, in this case, we get, I guess I wrote here, you get x1, x2 is equal to x2, x5, x4, and then x1. So it's not any more pentagon relation. It now the relations become it can be longer. So we have commuting relations, they still look the same, but then these relations can have longer expressions. Okay. So that was, so this is example, so that was the point of of the pictures, semi-invariant pictures for valued quivers, which is the main difference between simply laced and non-simply laced. For in simply laced, you cannot have that. Okay. And now, as I said, I want to talk about the theorem, which will talk about green sequences and for subsets, maximal green sequences for subsets, and Coxeter elements also related to subsets. So now I want to, and I mentioned at the beginning that there is some condition, so I just want now to say which condition I want. So here it is. So Q is a modulated quiver, not finite type, not necessarily finite type, so it's a modulated quiver. Now set S of modules, again, I'm labeling them with the positive roots. So set S of modules is a sequence of indecomposable representations. I should have said here exceptional, so that there is uniquely determined. I should add exceptional. So that the dimension vector uniquely determines module. Okay, so it is a collection of modules which satisfy the following properties. S is closed under submodules and quotients. No condition on extensions. It's only closed under submodules and quotients. And for each MJ, all indecomposable submodules and quotients come before MJ. So this is a sequence. So if my module is here, then its submodules and its quotients must come before that. That's ordering. And the other thing is that for each pair of modules in S, at most one x1 is non-zero. So you can have x1 one way, but not x1 the other way. Okay. So these are conditions that we have on the set of modules. So here are some examples. So I'm looking at the quiver, this tame quiver 1, 2, 3. Oh, okay, on left side, I just realized. On left side, I'm looking at my standard A3. So S can be S1, S2, or it can be S1, S2, P2. Notice I'm not here, I don't have all the simples, I just have 2 simples and P2, but both submodule and quotient of P2 are come before that. Or S can be S1, S2, P2, S3. Notice S3 is simple, so, but it's not a factor of P2, so it is okay to have it afterwards, but S1 and S2 must come before P2. So that's one example. And here, this is one that I will be using actually to illustrate a lot of things. So here we are in infinite type, S1, S2, S3, P2. I'm not taking P3, and I have here module 1, 3. Notice that I'm taking something in. Yeah, so when we say extension here, I have to be careful. I said for each pair module, at most x1 is non-zero. This is in S. So even though the extension, you may have the extensions both ways, but in the set S, we are not going to keep both extensions. So this at most one x1 non-zero, meaning in S. So I can have this extension, but if this is S2 and this is 1, 3, and this is S, so I could even allow this module, but I cannot allow both of these. So that is what it means, at most one extension. Okay, so it can be like that. Okay, let me just have it a bit more. Okay, so this is an example. And now a remark. which will be used for the theorem. I just want to check 1022. Okay, so the remark is if M is in S, so I have that quiver, finite, infinite type modulated, and I have collection of S as I described above. So if M is in S, then all simple composition factors of M are in S. Okay, because they're either submodules or quotients of submodules and so on. So all simple composition factors of module M must be in S. And now we define picture for S, which will be just as we expected before. So picture for S will be, we take d of beta I. So S is given with modules which are given with positive roots, beta I. So d of beta I is defined just as before. Euler bilinear pairing is 0 and Euler bilinear pairing on submodules is less than or equal to 0. So this is just as always these domains. We take union, but now we take union of beta i's only over the set S, and then intersect with Sn minus 1 so that we have all these nice spheres that we can draw. Okay, and also we can see orientation on the spheres. Okay, so the remark is that this LS as defined here is still a picture. So it is a subcomplex of a triangulation of the sphere Sn minus 1. Normal orientation on Sn minus 2 simplices. Notice because it is Sn minus 1, I have to look at n minus 2 simplices, which are like, codimension 1 simplices in Sn minus 1. Normal orientation still comes exactly from normal orientation of d beta I. So we just keep that normal orientation. If beta I is on one side, it's positive and so on. And rotational orientation is on n minus 3 simplices is again the same rotational notation that we defined by taking the cluster tilting object with n minus 2 summands, and we take the perpendicular category. In that perpendicular category, we take the simple objects, and simple objects correspond to 2 of these, and then we decide in which order we take them. So it's this rotational orientation is given exactly as it was given for the semi-invariant pictures, and it is projected. When we project it, you can still view it as concave one way, concave the other way. And now a green sequence is a sequence of crossing walls, d beta i's, from positive to negative side, which is just like crossing from positive C vector to negative C vector. So it's the same idea. Okay. And okay, so here I will use these 3 examples later. So okay, so this is one example where my for S, I just took these 3 simples. That's a simple little S. Or I could take my S to be these 3 with P2. That's another S. Or I could take S by adding 3, 1. Or we could continue. We could make longer and longer and longer S's, okay? Now, with each one of these, we can talk about maximal green sequences. So when my S is just this, well, I have 6 maximal green sequences, right? You could go this way or this way, this way, this way, this way, this way. So there are 6 maximal green sequences. Now, if my S, if I add P2 here, then some of the sequences stay the same as this. This one is essentially this one, but notice we get this one new here because now we have P2 here, so we get another maximal green sequence. So here we had 6 of them, here we have 7 of them. Now, if I add 3, 1, I said we can possibly add another module, then you can see that you're getting more maximal green sequences. I think I think I drew all of them here. I think there are 10 of them, and I drew all of them. And you can keep doing, and you will be getting more and more maximal green sequences. And now the question is, how does that correspond to what I was talking about Coxeter? So let me now talk about Coxeter. But I just want to mention that at the very end, or towards the end, I will be talking about maximal green sequences for this infinite representation. And this one has actually only 5 maximal green sequences. So what will happen is that some of these maximal green sequences will survive throughout the process, and some of them are going to get longer and longer and longer and never stop, and cannot be maximal green sequences, will become infinite green sequences, so they won't be maximal green sequences. So that's why I have this picture here, and as I said, I will be going back to this example at the very end when I talk about maximal green sequences, really for this quiver. But now let me talk about Coxeter. Okay, so I have my set S given with these modules which satisfy nice properties. I have LS, a picture, which is the domains of I like to call them domains of semi-invariance, the betas. And then we define a picture group by taking X to be all X's which appear in the beta. So you can see you actually get X beta i's for each one of the beta i's that appears here. So the group will be generated with all of these. That's not the minimal set of generators, but it is a set of generators. And then we get relations for each n-2 simplex by going around the n-2 simplex and reading off, reading off, reading off. Okay, and this is how you get the group. Okay, now a quick remark. S contains simple composition factors of m beta i's. I already mentioned this earlier, that all simples which are composition factors of m's must appear here. So now we have admissible ordering on these simples. So we only look at the simples which appear here, and we look at the admissible ordering. So if I'm back here, right? If I'm here, I have only these 2 simples. So you don't always get all the simples. I get these 2 simples, and I consider this to be admissible ordering, which is coming straight from the quiver. And the quivers are no, did I write acyclic? I mean, all my quivers are acyclic. Yeah, maybe I forgot to mention, I mean, everything is acyclic. Okay, so now Coxeter element in the picture group is the product of x's corresponding to these simples in the admissible ordering coming from the quiver. So as I1, I2, as which are these are the simple modules, and we write them in the admissible order, just the way Coxeter is written in general. And I write C, but the C is really depends on S, right? So it really depends on S. Okay, and now I'm just restating the theorem, and then I want to discuss a little bit about the proof. I'm just checking time. Okay, so the theorem says let Q be an acyclic quiver. Oh, okay, I wrote here acyclic quiver, modulated acyclic quiver. Let S be a finite subset of indecomposable exceptional modules satisfying condition star. So this condition star is that we put submodules before the module that in S, one extension is there, but the other is not. One extension might be there, but the other is not. And what was the third condition? I had a third condition. Yeah, I mentioned this. Oh yeah, it is closed. Yeah, actually the condition 2 implies condition 1, but I think I just felt like it's nice to mention condition 1 just to kind of make it clear that, yeah, you have to have submodules and quotients there. But this actually implies that. Okay. And so now the statement is that there's bijection between maximal green sequences in the picture of S and positive expressions of the Coxeter in the picture group. And now I want to discuss a little bit about the proof. I won't do all the details, but just, okay, so here is, let me do this way so that I can. So here's my set S and the modules. Here are the simples in here. And then the Coxeter is the product of x's corresponding to these simples in admissible order. And if I start with maximal green sequence, I want to see positive expression for the Coxeter. So one way direction, one way is quite clear. I take maximal green sequence. Now maximal green sequence, I sometimes denote by G, even though maybe G is really bad letter because G is usually used for G vectors. I just realized I should have not used G. Okay, but maximal green sequence is a collection of walls that we cross. So this is how I like to think about maximal green sequence. And then to that sequence, we associate element where we multiply x beta 1, beta j1, x beta j2. So we just take x's in the same order that they go here. And then the claim is that this element, which we now got in the group, that this element really is equal to the Coxeter element, which is up here. Okay, so I'll just show first on the example, and the proof actually goes kind of the same way, but formally, okay? So here's this example that I already talked about. This is just my little A3 with P. Well, no, actually it can be, yeah, this example actually can be on A3 or it can be on the big infinite type, okay? And I'm taking the G1 to be this maximal green sequence, which is just x1, x2, x3. So this is precisely the Coxeter. And now I'm taking my G2 to be ds2, dp2, and ds1, and then ds3. And that corresponds to this element here, which I wrote here. And now this part here, S2, P2, S1, S3, P2, S1 is precisely the relation that we have in the picture group, which is coming from here, right? Either we read them in this order by putting inverses here, or you say this is equal to that, which is the same, right? So this gets replaced by X1, S2, and that is precisely the Coxeter. And this is what you can do for any maximal green sequence. If you do this, well, you have to cross one way, the other way. But the idea it uses that any crossing path gives product. Yeah, one way of saying is that any crossing path gives product of elements in the picture group. So if you do any crossing, what you end up here is the product of the paths of the walls that you pass, and that this is well defined. So that is, proved. So this is a way that you can see, or you can easily see an example. Now, the other way, the direction the other way is a bit more complicated. So I want to talk a bit more about that. So now I want to say, if I start with an expression here, which I could so call it C sub phi. Oops. Then I want to show that there is this maximal green sequence, which is going to give me that C. So I'm starting with my S. Here's my S, and it will be induction on M. So if M is equal to 1, then my set S is just M beta 1. If it is M beta 1, notice simples have to be there. So if there is only one of them, this must be a simple. And if there is just one and it's simple, D beta D for a simple is a circle. So the maximal green sequence, we have only one maximal green sequence going this way. And of course we have for Coxeter, we have this. So for n is equal 1, it's clear. And now we say, suppose this is true for m minus 1. So it's true for a subset without the last element, without last m. Okay. Then we want to prove that it's true in general, right? So first we look at the pi, which is a group homomorphism from the picture group of S to the picture group of S prime. Now, which is defined by sending X beta M, so it's the last beta, see, last beta in the sequence. Okay, where's my S? Yeah, so we are going to send X beta M to identity. So pi of X beta M is identity. Then first of all, we show that pi is an epimorphism. And this follows, okay, if beta M is a simple, then this simple doesn't appear anywhere else. So S prime has modules which don't have that simple. So you can never, by eliminating this simple, you don't eliminate any of the other words that appear here. If X beta is not, doesn't correspond to simple, you can never use a longer word to eliminate the simple thing. So all the simples are going to stay here. All the X's corresponding to simples are going to stay here. So that's essentially idea why it is epimorphism. So it is an epimorphism. And then the other thing is, again, that it takes Coxeter to Coxeter. So if this is a simple, then Coxeter in S will have that simple. But then when you go here, this one doesn't have the same SM because we are eliminating that. And the Coxeter here will have the other simples. So Coxeter from here, after you eliminate XM, I mean beta M, X beta M will just stay to be Coxeter here. Okay. So whichever way, it will stay as a Coxeter. So this is important with Coxeter and Coxeter. So this is how we want to use the induction, okay? And now proof of the theorem, okay? So here's the Coxeter, which is I1 up to IR, and pi of that Coxeter is again Coxeter, which is, okay, now this Coxeter, this is on the smaller quiver. It corresponds to the green maximal green sequence on the smaller quiver. Now, if X beta M does not appear in the expression, so here I'm looking at my expression, okay? So I'm looking at X beta M. So X beta M is the last one in S. Maybe let me just write here on top. So my set S is M beta 1 going up to M beta M. Okay, so beta M is this very last one. And this is x beta m is x corresponding to that. Okay, so here I'm starting with the Coxeter, some expression of Coxeter in the big quiver. I will be referring to big quiver and smaller quiver just to know which one I'm talking about. Okay, now if x beta m does not appear here, then this is this expression is just the expression over the smaller quiver. And if it is expression over the smaller quiver, then it corresponds to a maximal green sequence. And then this maximal green sequence over the smaller quiver will stay as maximal green sequence over the bigger quiver. So that's the first step. So if x beta doesn't appear here, then whatever you have here gives you Coxeter here. This Coxeter gives you maximal green sequence. Maximal green sequence stays as maximal green sequence, and that's fine. So that is one way. Now the other thing, the other comment is, if this m beta, again, m beta is the last one. If m beta is simple, then x beta m appears, and okay, if m this is simple, then this will appear in the Coxeter, because as I pointed out, the Coxeter has to have x's of all simples which appear, right? So if this is simple, then x beta m will appear in this Coxeter. And since simples are since this simple is last in my S, it commutes with everything here. One has to think a little bit about that, but it commutes with everything here. And here is how you're going to construct the maximal green sequence, okay? This is, I mean, formally written in the paper, but okay, so here's the Coxeter on the big quiver. Here's my x beta m, which appears somewhere here. These are all, oh yeah, there's another lemma which says that the same letter cannot appear twice. So if this x beta m is here, it is not anywhere else. So here I have x beta m. So I have these and these elements which are on the smaller quiver. This sequence corresponds to a green sequence like that. Then x beta m, then we take x beta m, and because, as I pointed out, x beta m appears everywhere, you cross x beta m. You have to start, maximal green sequence has to start outside of all the circles and semicircles and everything. So I have to start here. So first I take this part of the maximal green sequence, then I use this x beta to cross into the inside of the d beta, and then I continue with this, and this is how you get the maximal green sequence. And similarly, but it gets a bit more complicated if m beta is not simple. So here it was easy because since it was simple, I knew that there were no submodules and no quotients before or after. So it was kind of very, very, it's easier because it's simple. I don't have to worry about other things that happen here, okay? Now, if m beta is not simple, then again, and I assume it appears here, then there is a certain part of the quiver that one has to be careful about. But again, you get a piece of the maximal green sequence, piece of the maximal green sequence. You have to be a little bit careful in proving. I mean, I'm just saying that the proof is requires a bit more, and you get again, you have maximal green sequence on the subquiver and use induction and get maximal green sequence here. So the idea is, as I said, for this pops, for the simple, you see, if x beta is simple, it is really a circle, and this is really, really good picture of what's happening, okay? If it's not simple, it is just that this part becomes a bit more complicated. You have to look at the smallest submodule of m beta and largest largest, the last quotient of m beta, and then look at a certain part here which will correspond to this. But you can still, I mean, the proof has that part. I mean, the proof is done, you know, properly. I mean, the proof is written properly, how you handle this. But as I said, in this case, it does become a bit more complicated. And that finishes that, okay? And now, 47, okay. So I just have a couple of remarks, so maybe I will finish a bit earlier. I was planning to try to finish a bit earlier, okay? So the remark, okay, so in short, for each subset S, we have the theorem which says, okay, let me just go back to the theorem. Well, I guess it's also stated here. Yeah, that for each subset, finite subset of indecomposable exceptional modules, we have this correspondence between maximal green sequences in the picture and Coxeter expressions in the picture group, okay? And I gave an example when we were increasing this set S, increasing this set S. So now I want to discuss a little bit about that. So remark, here's my remark. Okay, so here's my Q, which is not of finite type. And then I gave this example of one S, another S, another S. This had 6, this had 7, this had 10, and the number was increasing. And now what we know that for this quiver, there are only 5 maximal green sequences, right? So as I said at the beginning, some of the maximal green sequences which we had at the beginning stay as maximal green sequences, and some disappear since they get infinitely long. And here is a kind of picture of illustration of that. So let me just explain a little bit more on this picture, right? So this was my S1. I guess I didn't write. So this was D, I should really write D of dim S1, but this was my S2. I mean, again, D of that. This was S3. This was the P2, which is 2, 1. This was this module 3, 1. And those were maximal green sequences. And now in this final stage, these are the maximal. So what I'm writing here, these are the maximal green sequences which become stable, and they are maximal green sequences for the entire quiver. And I drew here this part, which is actually, notice that all of the green, maximal green sequences are outside of that region. And this is the region which is called inescapable region, because once you get in here, you can, if you get into this region, you cannot get here. And the reason you cannot get there is, here's the other picture, because there's the null root here. So there's this inescapable region, which tells us that none of the maximal green sequences can go through this yellow region, because then if they were to go through that, they would have to go through the null vector, and null vector is not one of the positive roots, so we cannot flip through the null vector, okay? So from the infinitely many maximal green sequences which we had at the beginning, okay, we have only these 5 which kind of stayed, and the other ones were getting longer and longer if you're adding more and more modules, but they become infinitely long, and they are not maximal green sequences here. This is the null vector which we have here, okay? And that is, so this is how, so what we are analyzing and what we would really like to see how to use these increasing sequences of acids and which are the good acids to look at. And oh yeah, and something else which I just forgot, this inescapable region I wrote here, it's bounded by, this is P1, this is P2, this is S3, and this is S2. So this inescapable region is bounded by the two smaller projectives and two smaller injectives. So this is what kind of defines, this is what we're doing actually with Steve Hermes, where we create this inescapable region, and it is given in terms of the null vector. So yeah, this I'm not going to go through that, but this I'm including this part which talks about so when you have this collection of disjoint embedded disks with boundary, so you want this boundary to be the links, the links that they were talking, and then you look at the free group and you take the commutator, and then the K-slice is collection of surfaces in D4 with these boundaries that we start with links, so that, and then you get the group, which is the pi, which is pi 1 actually of this space. So what you want, you take the big disk, you remove the link, and then you look at pi 1 of that, and that's G. That's how they actually started defining G. And this is how we also want to talk about when we start with G and we create picture space, is kind of going the same way, because we create picture space to have the same pi 1. So that's the idea. And then the K-slice is a collection of these surfaces, and that, okay, they're related to this lower central series, and that is where you have these Milnor invariants, which are the elements of the homology or cohomology, and that's where they prove the conjecture. But as I said, it's not, I mean, for us, it was more, looking at the pictures and looking at the pictures in relation to maximal green sequences and domains of semi-invariants and so on. And I think okay, so I decided to, I was planning to stop a bit earlier, so I stopped 5 minutes. I think I'm stopping 5 minutes earlier. So I should say thank you.
Thank you. So for questions, maybe we'll start with the people in the room, and people who are remote can type their questions on the chat. So Bethany, so yeah, I think you should be able to speak from there.
Can you hear me, Gordana?
Yeah.
It's Bethany.
Hi.
Hi. Okay. I had a question. Suppose you took a quiver of finite type, a Dinkin quiver, then do you know how many possible sets S there could be?
Huh. I didn't think about it, but yeah, that's kind of a natural thing to ask. So your question is, if we start with a finite type, right? How many these good sets S? I don't know. I didn't think about it.
Okay.
Yeah.
Well, second question, if that's okay.
Sure.
You said that it's more of a technical question, just to understand this X restriction. So you say that the X in S can only be non-zero on one side, one way.
Yeah. So that is exactly, you see, in this case, yeah, actually this one.
So are you assuming that the X?
You see, I'm allowing this as S, but there is no module which is extension of S. I mean, there is a module in the module category of extension of S2 by S3, but that module is not part of S. So or you could allow possibly one extension one way, but not allow extension the other way, even though in the big module category, you may have extensions both ways.
What happens if the X group is two-dimensional? Is it all possible extensions that appear as a middle term?
Can you say again? If the what is three-dimensional?
If the X1 group is two-dimensional, what happens then? Are you saying that all the possible middle terms in all the extensions must be in S?
I'm sorry, can you repeat? I hear kind of every pieces of words, and I'm not sure that I understood what you said.
So taking two objects in S, and then looking at all the modules which could be extensions of those.
Yeah. So the question is, can you include them? Is that what you're saying?
So I'm trying to get the precise statement what the X in S means.
Oh, you're trying to get, is this? Wait. Huh? Is this what you're trying to, is this what you're questioning?
Yes, okay, so I guess you're saying that.
Okay, so what I'm saying is, okay, so there are like several, okay, for each pair, so you take a pair of modules, okay, there are possibilities that neither of the X are, that both X are non-zero, okay. Now it's possible that both X are, that one X is non-zero, one is zero. Even if X in the category is non-zero, you may choose not to put the extension, just as I did in this one. Notice I did not put the extension of 2 and 3, okay? Or I did not put extension of S2 and this, okay? Now, if I could have put one extension, but not put the other extension, if there is extension, if I have M and N, and there is extension this way, and N and M, and there's extension this way, I can put one of them in, but I cannot put both of these in.
Okay, yes, I think that's thank you.
Okay.
Two extensions like that with both in S, that's the restriction.
Mm-hmm. Okay.
So what happens if you have two different extensions the same way round? Can both of them be in S or not?
Oh, you mean if you have two different extensions?
Well, I guess it's equivalent, isn't it? No, we can have.
The wave condition
V is written in the same dimension.
That's why it doesn't matter.
Let's see, if you have two different extensions, I think let me try to remember, but I think you can choose, if you have several different extensions, I think you can take only one but not the others. I think so. You could choose only one of them. Yeah, I think so. I'm not sure, but I think you can choose only one. Okay.
Are there more questions from people in the room?
Hi, Gordana, I have a question about your last example where you have this infinite type with only 5 maximal green sequences.
Yeah, here.
Right. So is there a finite set S which realizes all 5 of them?
Oh, is there a finite set which realizes exactly all 5 of them? Is that the question?
Well, I don't mind if it realizes more, but do these 5? They should be, right? There's this.
Yeah, because if you start with with the simple version, let me just go here. You see, actually, the way I drew this, that is the same. Oh, you mean? So I think of let me go back to that picture. So your question is, which finite set would give you exactly these 5, right? So I think if you take, if you take, there is, yeah. So you can, so if I include this, and this, no, I don't know. So the question is there a finite set that will give you exactly these 5, meaning crossing this and crossing this? Right, that's the question. I don't know. So is there a finite set of S that will give exactly these 5? I don't know.
Okay.
I believe yes, but I'm not sure. Okay.
I have a question. So if you take, so if you collect all the modules that you will meet by when you cross walls in these 5 maximal green sequences, is there any unique way to complete that set of modules so that it becomes a sequence S? Like a unique minimal way of to complete that set of modules so that it becomes some S to start with to define the future. And the only requirement is that this S should be closed under taking quotient and submodules, right? So it seems that there's a finite set you can do. I'm not sure.
Is there a way? I'm sorry. I'm again trying to. I'm really having hard time. Is there? So the question is, if you start with this finite. So are you saying start with a finite set of with these fine? I don't understand what was the question. Can you say again what was the question? I'm sorry.
So let's just take the example the last example you have here, and so you said that there are 5 maximal green sequences.
Yeah, you mean this one?
Mm-hmm. Yeah. Yes, this, and for each such a maximal green sequence, you'll have finitely many modules that you will meet when crossing walls.
Yeah.
And you just collect all those modules you will meet, and that is a finite set.
Okay, but you see, okay, what happened is we crossed this, right? We crossed these, but then if you take, then if you go back to the picture that I originally, right, this picture, right, this is exactly the picture where I took exactly those walls that I have at the end. This is my P2 and my I and my 3-1. But you get, once you have this, because of this crossing here, you end up creating different sequences, different maximal green sequences. So, so with these walls, I mean, at the end, I had these 5 maximal green sequences. I took those walls, right? These are the walls that they were crossing, but then you get more maximal green sequences there because some of these maximal green sequences, which happen to be now with these walls, if in the big algebra, because there will be infinitely many walls coming here, they will become infinite sequences of green mutations, and they will not be maximal green sequences. Oh, okay. I have a comment on page 6. If you write 6-term relation with square root of the generator for short root as x1, x2 square and x2, then it reduces to, oh, that's interesting.
So yeah,
Thank you, Tomoki.
Okay.
Yeah, that's, yeah, that's, yeah, I mean, we didn't think about in those terms, but that looks like something that we should, so is that coming x1, x2 square, x2 square, x3, x4, also x4 square. Actually, I don't understand exactly how you're doubling an arrow, which are you doubling an arrow which was a valued arrow? Is that what happened?
As I wrote, if you just take the square root of your generator for short root, there are actually 2 short root this case, right?
Yeah.
And then this relation is reducible by pentagon relation.
Okay.
Yeah, it is written in my recent paper, so please look.
Oh, is that in the paper that you just finished? Okay. Yeah. I didn't see. Okay. That's
Okay.
nice. That's nice. Okay.
Yeah, just a comment. No. There's no nothing opposing to your statement. Okay.
But okay, but no, it is nice. So would you say, would you say that all the relations that are coming with valued quivers, is that in the, okay, is
Right,
it
that's
your
right.
paper that all
Yeah,
relations in valued quivers can be reduced to the pentagon relations?
That's right.
Oh, okay. I'll check. I didn't. Okay, I'll check that. Okay,
Yeah.
thank
So
you
for
very much.
G2 case, for example, G2 case, you take as a not a square root but a triple root. How to say cube root? What? Yeah.
Okay. Thanks.
Dixie had a question on the chat. Would you like to unmute yourself and ask?
Yeah, I'm reading it. Can it be that S is an exceptional sequence? If so, can you say anything about the cases of the main theorem when S is a complete exceptional sequence? Okay, I obviously do not. Okay, so can it be that S is an exceptional sequence? It can be, but it's not. No, I think that the example, this example is not exceptional sequence. So I think it might be interesting to see what one gets, okay, given an exceptional sequence, can it be arranged to satisfy this ordering Well, okay, I don't have answer, but the question about how it can be done with exceptional sequences or complete exceptional sequences, because obviously some of these are not exceptional sequences. Some of them I have to rearrange to have exceptional sequence, right? But it's interesting question. What can one do if one takes S to be an exceptional sequence, possibly rearranged?
Are there
Okay, yeah.
Are there more questions from online participants?
Okay, so there are these two questions online, right? I mean, comments, actually, Tomoki's comment is not a question, it's a comment. Okay.
Well, let's, if not, then let's thank Gordana again for the wonderful. For the second lecture, it will be at the same time next Wednesday.
Okay, thank you. And I will send abstract a bit earlier.